What's the most common reason an irrigation system doesn't perform the way it should? Most people point to broken sprinklers, but the truth is it comes down to one of four elements: pressure, nozzles, placement, or condition. I'm Dr. DeBusk, and in this presentation we're going to walk through each of these four elements. We'll look at how sprinkler pressure affects coverage and use, how nozzle selection and adjustment make or break uniformity, how placement strategies determine whether turf or landscapes get even water, and finally, how the condition of the sprinklers themselves can cause issues that often go unnoticed. By the end, you'll see how these four pieces work together and why paying attention to all of them is essential for efficient, effective irrigation. Before we zoom in on nozzles, let's step back and look at the big picture. There are three simple principles to follow when it comes to sprinkler pressure. First, the operating pressure has to be right for the nozzle. Second, it needs to be right for the sprinkler placement. And finally, sprinklers that require different pressures should always be placed on separate zone valves. Keeping these three principles in mind makes the difference between a system that's efficient and one that wastes water. Here's where pressure really matters: the nozzle. Think of the nozzle as the heart of uniformity. Each sprinkler type, brand, or model will operate across a wide range of pressures, but manufacturers design them for just one optimum pressure. The top table shows the general pressure ranges and the optimum pressure by sprinkler type. If the pressure is too low, water coverage drops and the plants don't get what they need. Too high, and we end up with waste, poor distribution, and increased costs. That's why nozzle charts are so important. They tell us the sweet spot, the minimum, maximum, and most importantly, the optimum operating pressure. Notice that for the Toro Precision Spray nozzle, the optimum pressure is 30 psi, while for the Hunter PGP nozzle, the optimum pressure is 45 psi, as shown in bold on the manufacturer's chart. There is also a range for the minimum and maximum pressure. One other thing to notice: flow rate goes up with pressure. For example, a Hunter 2.5 nozzle is typically expected that it will flow at 2.5 gallons per minute, although it flows at 1.7 gallons per minute at 25 psi and almost 3 gallons at 65 psi. That's a 40% difference. You can see how easily water scheduling gets thrown off when pressure isn't correct. When we talk about pressure and placement, the key concept is sprinkler radius, the distance water travels from the nozzle. For proper coverage, the water needs to reach from one sprinkler all the way to the next. That's what we call head-to-head coverage. Manufacturers give us nozzle charts to show how far a nozzle will throw water at different pressures. That way we can design for the right pressure to get consistent coverage. Here's a real-world example. Here is the Rainbird 5000 rotor chart. A Rainbird 3.0 nozzle throws 36 feet at 25 psi, 38 feet at 35 psi, and 40 feet at the optimum 45 psi. At 55 and even 65 psi, it still only throws 40 feet. That's because higher pressure doesn't mean farther distance. It just means more gallons per minute are coming out. So if you place sprinklers assuming 40 feet at 25 psi, you'd actually end up short, leaving dry spots. Now let's look at what happens when pressure is off. Low pressure creates too many large droplets, and most water falls near the sprinkler or at the very end of the stream. The middle gets skipped, leaving behind the dreaded brown donut patches of turf. High pressure creates the opposite problem: too many small droplets. That's when you see fogging or mist rising off a spray. The result is poor distribution, wasted water, and stressed plants. Sprinkler pressure isn't static. It changes over time as landscapes grow, systems age, and water sources fluctuate. At night, when many irrigation systems run, pressure can drop 40 to 50%. That leads to drought stress even if it hasn't been dry. That's why it's so important to check systems at least once a year. High pressure is relatively easy to fix with regulators or pressure compensating parts. Low pressure is trickier. It usually means investigating the source, pipe sizing, or flow rates. Pressure can be regulated at the source, zone valve, sprinkler, or even the nozzle itself. Nozzles may look like small parts, but they control how water leaves the sprinkler. and that affects everything from coverage to conservation. They're the second of the 4 critical elements that determine uniformity. There are 6 principles to keep in mind when selecting and managing nozzles. First, they have to be correct for the pressure and correct for the placement. Next, they should apply water at a matched precipitation rate, meaning the flow matches the area being covered. Also, the total flow of all nozzles in a zone has to stay under the limits of the source and components. Additionally, we adjust the radius to avoid unnecessary overflow. And finally, the nozzle trajectory has to be correct so the spray pattern isn't blocked or distorted. When these principles are applied, you get nozzles that save water, reduce waste, and keep coverage even. As mentioned earlier, nozzles only work their best at the right pressure. If a nozzle is running above or below its optimum, the water won't break up properly and coverage suffers. A common mistake is mixing spray nozzles and rotor nozzles on the same zone. Sprays like lower pressure around 30 psi, while rotors usually need closer to 45 psi. If both are on the same line, one of them will always be operating poorly. That's why it's important to separate sprinklers that need different pressures onto different zones, or use pressure regulating bodies and valves to get the system back in balance. Let's look at 2 common real-world examples. Situation 1. The system has both rotors and sprays on the same zone. If it's set for 45 psi, the sprays are way overpressurized and coverage fogs. If it's set for 30 psi, the rotors underperform. The right solution is to separate them into different zones or to use spray bodies that regulate down to 30 psi. Situation 2. There are separate zones for rotors and sprays, but the source pressure is high enough that the sprays are still running at 45 psi. In this case, the rotors are fine, but the sprays fog and waste water. The solution is to add pressure regulation at the spray zone valves or switch to pressure regulating spray bodies. These are issues technicians run into all the time, but with a little pressure management, the fixes are straightforward. Spacing matters just as much as pressure. If sprinklers are placed close together, it's better to use a nozzle designed for that spacing than to force a larger nozzle to work by radically adjusting the radius down. For example, in a 15 to 16 foot area, spray nozzles are a better fit than small rotors with breakup screws turned way down. Coverage problems also happen when nozzles can't throw far enough to reach head to head, or when they throw too far and waste water outside the target area. The goal is always the same: choose the right nozzle for the spacing to keep coverage even and water use efficient. Uniform coverage doesn't just depend on spacing and pressure, it also depends on precipitation rate, which is how much water is being applied to each square foot. Matched participation rates, or MPR, means the flow of each nozzle is proportional to the area it covers. If a quarter circle nozzle flows 1.5 gallons per minute, then a half circle should flow about 3 gallons per minute, and a full circle should flow about 6 gallons per minute. That way, all areas get the same application rate no matter the arc. If all 3 nozzles had the same flow, the quarter circle would end up twice as wet as the half circle and 4 times as wet as the full circle. That's wasted water and poor uniformity. Nozzle charts are our roadmap for uniform coverage. They give us the operating pressure, the throw radius, the flow in gallons per minute, and the precipitation rate for both square and triangular spacing. Manufacturers make it even easier by building matched precipitation rates into their spray nozzles. Here's an example from the Irritrol iPro nozzles. At 30 psi, a 15-foot half-circle nozzle throws 15 feet, flows 1.82 gallons per minute, and applies about 1.56 inches per hour at square spacing. But notice that a quarter nozzle, half circle, and full circle all apply at about the same rate, around 1.6 inches per hour. Even when radii are different, precipitation stays close, about 1.8 inches per hour. The result? We can use different arcs and radii together on the same zone valve and still get uniform coverage, because the flows are matched to the areas they cover. There are a couple of exceptions to keep in mind. Short radius nozzles, like 2, 4, or 6 feet, often have precipitation rates 2 to 4 times higher than the standard NPR nozzles. These are specialty nozzles, and you don't want to mix them with regular sprays, rotors, or rotating nozzles. Some variable arc nozzles can also throw precipitation rates off, so use caution if you're mixing them with fixed NPR sprays. Here's a practical example. With Irritrol iPro nozzles at 15-foot spacing and 30 psi, the quarter circles flow 1 gallon per minute. These are letters A, C, D, F, G, and I. Half circles, 2 gallons per minute, letters B and H. And the full circle, 4 gallons per minute, letter E. That proportional flow keeps the precipitation rates right around 1.56 to 1.60 inches per hour across all nozzles, giving us perfectly matched coverage. Let's compare rotating nozzles and rotor nozzles. Rotating nozzles are straightforward. They're manufactured with matched precipitation rates already built in, just like spray NPR nozzles. That means coverage is even across arcs and radii, with only minor differences between brands. Rotor nozzles are trickier. Only a few residential models come with built-in NPR. For most residential and commercial systems, technicians have to manually match precipitation rates. That means making sure the gallons per minute of each nozzle is proportional to the arc it's covering. Otherwise, some areas will be drenched while others dry out. Here's an example using a Hunter PGP Ultra Blue nozzle chart at 45 psi. We've got a zone with 4 quarter circle sprinklers and 2 half circle sprinklers. Since the smallest arc is a quarter circle, we start there. The 1.5 gallons per minute nozzle throws about 31 feet at 45 psi. So that's our match. All 4 quarter circles get 1.5 gallon per minute nozzles. The half circles cover twice as much area, so they need double the flow, about 3.0 gallons per minute nozzles. If we had a full circle, it would be 4 times the area of a quarter, so it would take a 6.0 gallons per minute nozzle. For odd arcs, we figure the full circle flow first, then divide. For example, if the full circle is 6.0 gallons per minute, then a 1/3 circle would need 2.0 gallons per minute. That way, precipitation rates stay matched across all sprinklers in the zone. When we select nozzles, we also have to think about the system's flow limits. It's not just about the nozzle, it's about whether the main line, lateral lines, valves, and the water source itself can handle the total flow. Here's an example. Say we have 2 half-circle rotors with 3.0 gallons per minute nozzles and 4 quarter-circle rotors with 1.5 gallon per minute nozzles. The total flow is 12 gallons per minute. That flow has to be within the source capacity and the system's components. If the flow is too high, pressure drops throughout the zone. And as we've already seen, poor pressure is one of the top reasons for poor coverage. That's why a technician always measures operating pressure, checks available flow, and calculates the total zone flow before making changes. When sprinklers are first installed, it's common for them to throw water too far, into the street, onto a driveway, or into the neighbor's yard. The goal is to adjust the nozzle so it throws just slightly beyond the target area, usually no more than about 2 feet to allow for wind drift. With spray nozzles, the radius screw doesn't really work well. If the radius needs to be longer or shorter, the solution is to replace the nozzle with the right size. Fixed arc nozzles that need a wider or narrower arc are replaced with the proper arc or with a variable arc nozzle if a fixed one doesn't fit. Variable arc nozzles or vans are adjustable, but they often get knocked out of adjustment by mowing. Rotors and rotating nozzles are different. They're all variable arc. The radius screw can reduce the throw, but only up to about 25%. Any more than that and you need a different nozzle. The arc is adjusted with arc stops, and if a rotor is running under low pressure, the radius screw can be used to help break up the stream mechanically, but you have to be careful not to reduce the throw too much. In most cases, it's better to fix the pressure problem at the source. Nozzle trajectory is simply the angle at which the nozzle throws water, and it can make all the difference in whether the water goes where it should. Most rotors come with an option for low-angle nozzles. These are marked with an LA and are designed to keep water streams under tree branches or to direct spray under shrub canopies. This gets the water to the soil where the roots are instead of wasting it on leaves or overthrowing onto sidewalks. The angle varies by nozzle size. 15-foot nozzles usually throw between 23 and 30 degrees, while a 5-foot nozzle may throw as low as 0 to 5 degrees. Variable arc nozzles usually stay between 23 and 27 degrees, regardless of radius. When working in shrub beds, a good trick is to use a 4-inch pop-up spray body with a flat or very low angle nozzle. That way the nozzle just rises above the mulch and delivers water directly to the root zone, with no tall PVC risers sticking out. Coverage doesn't have to be as exact for shrubs as it does for turf. If 60 to 70% of the root zone is covered, it's usually enough. The ultimate goal of irrigation is simple: getting water into the soil where the roots can use it. The more directly water gets from the nozzle to the soil, the better the uniformity. That's why drip systems are so consistent. They apply water right to the soil. Sprinkler placement is the third element of uniformity, and there are 5 principles to follow. First, the placement has to match the pressure and nozzles being used. Second, sprinklers must be placed so they overlap. Third, spacing should be consistent. Fourth, sprinklers should water turf separately from landscape beds. And fifth, don't mix sprinkler types in the same area. Of course, real landscapes are rarely perfect squares or rectangles. That means some sprinklers won't line up head to head, and there will always be some overthrow or underthrow. That's why adjustments at installation and later, as the landscape grows, are essential for the best results. The main factor in sprinkler placement is the nozzle radius at the operating pressure. Sprinklers need to be placed so that their coverage overlaps head to head, or else you'll end up with dry spots. That means the maximum spacing between sprinklers should equal the nozzle radius. Now, in real landscapes, dimensions aren't perfect. That's why we use a 10% rule. Sprinklers can be spaced within 10% of their radius as long as they're operating near their optimum pressure. Here's an example using K-Rain RPS 75 rotors at 40 psi. The zone needs to cover 33 feet in one direction and 35 feet in the other. Quarter circle sprinklers with 1.5 nozzles throw 33 feet at 40 psi. That just meets the minimum standard, since 35 feet minus 10% is 31.5 feet. The half circle nozzles use 3.0 nozzles with a 36-foot throw. Those will reach across the zone, but they'll need to be adjusted slightly to avoid too much overthrow. So this layout works with 4 quarter circle sprinklers at 1.5 gallons per minute and 2 half circle sprinklers at 3.0 gallons per minute, giving us coverage that's as uniform as possible. Sprinklers are not designed to work by themselves. Every nozzle puts down the most water closest to the sprinkler and the least water at the farthest point. That's why overlapping coverage is so critical. Head-to-head spacing means each sprinkler throws water all the way to the next sprinkler, but that overlap fills in the weak spots and keeps coverage uniform. If the pressure is right, we can allow up to about 10% variance in spacing. But if the pressure is lower than 80% of optimum, the sprinklers must be spaced closer, sometimes even tighter than head-to-head. Take a look at this graphic. You can see how each sprinkler throws to its neighbor, and those neighbors throw back. Sprinkler A throws to sprinkler B and to sprinkler D. Sprinkler B throws to sprinkler A, sprinkler C, and sprinkler E. Sprinkler C throws to sprinkler B and to sprinkler F. Sprinkler D throws to sprinkler A and to sprinkler E. Sprinkler E throws to sprinkler D, sprinkler F, and to sprinkler B. Sprinkler F throws to sprinkler E and to sprinkler C. That head-to-head spacing fills in the weak spots, since each nozzle applies the most water near itself and the least at the far edge. Overlapping ensures even coverage across the whole zone. This coverage arc diagram shows how many sprinklers apply water to each area. Notice the letters. They represent which sprinklers are watering that spot. Here's the key idea. Areas close to the sprinkler get the most water, but they also get the least from distant sprinklers. Together, the balance makes coverage more uniform. If these are rotors, the pause, or dwell, at the end of their arc adds a little extra water along the edges. Spray nozzles do the same thing by applying a bit more water at the edges of their spray pattern. Either way, overlap balances the rates and keeps things even. Corners are one of the most common problem areas. If sprinklers are missing, those corners only receive water from the very ends of other sprinklers. That's the weakest part of the spray pattern, and it's not enough to keep turf healthy. Corners dry out faster anyway because of heat from nearby pavement, water wicking from concrete, and soil compaction from traffic and mower wheels. In the top graphic, sprinklers are missing from the bottom corners. Notice how the corners with only sprinklers A and D on the left or C and E on the right are left weak. Since the last 15% of a sprinkler's radius applies very little water, these corners are prone to drought stress without extra rainfall or hand watering. The fix is simple. Every corner should have a sprinkler, just like the other side of the zone. An even worse example is shown in the bottom graphic. With no sprinklers in any corners, those areas only get the weak ends of one sprinkler each. The side edges get no coverage at all, and the middle ends up much wetter than the rest of the zone. A common misconception is that you can just extend sprinklers across the zone to make up for missing corners. In the example graphic, sprinklers D and E are adjusted to throw toward A, B, and C, but the coverage is still poor in the corners, and now water is being wasted outside the target area. Overthrow onto driveways, sidewalks, or structures can cause damage and stains. Even if it lands on landscaped areas, it can create problems with too much moisture. Adjusting across the zone is never a good replacement for proper sprinkler placement. There's one exception to overlapping coverage from all sides, and that's on slopes. Water naturally moves downhill with gravity, so sprinklers at the bottom of the slope aren't necessary. A common example is the narrow strip of turf between two houses. Instead of placing sprinklers on the property line, they should be installed along the top edge, overlapping side to side and covering each corner at the top. Gravity will move the water downhill, providing coverage at the bottom. Consistent spacing is just as important as overlapping coverage. In a large turf area, sprinklers placed at even intervals create more uniform results. In the turf spacing example, the part circle sprinklers along the edges throw slightly beyond the full circle sprinklers in the center, while the full circles reach across the width but fall just short lengthwise. Together, these two effects balance each other out, and the consistent spacing in both directions keeps the coverage uniform. The coverage circles in the graphic help you see how head-to-head spacing still works even when the dimensions aren't the same. Since landscapes are rarely perfect rectangles, irregular shapes require extra attention. In these cases, part circles sprinklers are placed around the perimeter while full circles fill in the center. The coverage diagrams show that some overthrow is necessary, otherwise the edges would be underwatered. This is a good example of how sprinkler performance and landscape design must work together. Overthrow in the graphic may look inefficient at first glance, but it's actually what ensures even coverage in odd-shaped areas. Sprinklers are built for certain radii, and understanding those standards helps improve efficiency. Spray nozzles typically range from 5 to 15 feet, rotating nozzles from 8 to 35 feet, and rotors from 20 to 35 feet. Each can only be adjusted down about 25%. If the landscape design matches the standard radii, less water is wasted and coverage is much more efficient. This concept is especially valuable during renovations when adjusting the shape of an irrigated area to fit the sprinklers can greatly improve water use efficiency. There's a misconception that sprinklers for turf and landscape plants can run on the same valve, just like rain falls everywhere. But that's not how irrigation should work. Turf and landscape plants have completely different water needs. Turf grass has shallow roots, usually 3 to 8 inches, and needs smaller, more frequent applications. Trees and shrubs, on the other hand, have root zones that are much deeper and broader, often 2 to 3 times the width of the canopy. They need water less often, but in larger amounts. If you try to water them together, one group is always going to get the wrong amount. That's why the correct design is to keep turf sprinklers on one valve and landscape sprinklers on another. This prevents plant stress and saves both water and money. One of the most important placement principles is to avoid mixing sprinkler types in the same area or on the same valve. Sprays, for example, apply water 3 to 5 times faster than rotors or rotating nozzles. And even within the same category, precipitation rates can vary between different models. Drip emitters and microsprays also apply at completely different rates. The key to good uniformity is consistency. All sprinklers in a zone should apply water at the same precipitation rate. Mixing types without careful calculations usually results in one area being overwatered and another underwatered. Unless you're highly skilled in calculating rates and nozzle performance, the safest practice is to keep zones limited to a single sprinkler type. The last element that affects uniformity is the condition of the sprinklers and the system itself. Many technicians only look for broken parts, but most issues develop gradually, like leaking seals or clogged filters, that quietly reduce performance. An average residential system has 40 to 50 sprinklers, and commercial zones may have that many just in one zone. If components drift too far from their original condition, efficiency drops, costs go up, and plant health suffers. The goal is to keep the system operating as close to new as possible. Most condition problems show up at the sprinkler itself. These include pressure or coverage issues, nozzles clogged with debris, arcs out of adjustment, or sprinklers blocked by turf or plants. Sprinklers can also sink, lean, or sit too high, which throws off coverage. Pop-ups may stick, rotors may stop rotating, or seals may leak. Even low head drainage or broken risers are common. All of these gradually reduce uniformity, even if they don't scream broken at first glance. Valves and valve boxes also cause problems. Valves can stick on, fail to open, or leak slowly. A sudden water hammer when a valve shuts can signal damage. Missing or broken valve box lids and poor wiring connections can also compromise the system. The controller and sensors are the brains of the system. Problems here range from display faults to insect damage, poor outdoor protection, or wiring without conduit. Even simple programming mistakes like wrong runtime, start times, or dates can waste huge amounts of water. Batteries, rain sensors, and pump start relays also need regular inspection. Finally, the water source itself can be the weak point. High or low source pressure, clogged filters, or a malfunctioning pump all reduce performance. Backflow preventers and suction lines also need to be checked, especially in reclaimed water systems where outages may occur. The point is, condition issues affect every part of the system, from the source to the sprinklers, and keeping components close to their original condition is the key to uniform coverage. We've now looked at the four main elements of sprinkler coverage: pressure, nozzles, placement, and condition. Pressure must be close to optimum so the radius and droplet sizes are correct. Nozzles have to match the pressure and spacing, and we use matched precipitation rates to keep coverage even. Placement requires overlapping, consistent spacing, separating turf and landscape, and not mixing types. And finally, the condition of the system, keeping sprinklers, valves, controllers, and the source in good shape, is essential. When all of these work together, the result is uniform coverage, healthier plants, and much greater water efficiency.